What were the three laws?
Objects, planets,
Get it in there? Good.
Monkey.
And then the times, the sweeping time.
So first one is that it's an ellipse. Okay. Second law was that the area swept out was the same on both sides, which pretty much tells us that the Earth moves faster when it gets closer to the sun. And that was the conclusion we drew. And the third law, we just had those formulas, okay? Again, the formulas, one of them gave us the period, or the length of time it takes for an object to revolve once around another central object. The second law gave us the orbital speed. So remember from last class, we ended with the third law, where the third law had two parts. The orbital period, which is the length of time for one revolution, and then the orbital speed. Okay, so we had two different equations now we're going to use today.
So is that an orbit? Every single thing has like a
Anything in orbit, correct.
Anything in orbit?
Anything that has a central object that is in orbit, absolutely. It's a governing law. Orbital speed is v, period. All right, let's get started. So let's say we have a problem here. We are told, let's see, that on a mission in Venus, let's say on a mission,
Mr. Hall, I have a question. Is Pluto a planet?
there's back and forth with the whole thing. Some say yes, some say no.
What do you say? I learned that.
I say that I'm not well informed enough to make a decision, to be honest. I don't know enough about the planets like Pluto's and what the characteristics are that classify them as yes or no. But I have heard both. I'm happy to entertain thoughts on them, but I don't know. Yeah, and that's why. I learned it as 9 planets. And now they're teaching like there's only 8 planets. So it's like, but just served us.
9 pizzas.
But there's no pizzas now, so it's just what? Just served us nectar. Nectar. Juice.
Why nectar?
Because it ends with N. It can't end with N. Like 9. Just served us.
9 pizzas.
You can't have a letter?
9.
What starts with 9?
Nectar.
I don't know, something good. I know nectar. That's what I'm like.
Just served us nuggets.
Yeah, nuggets.
Nuggets, there you go. Please write, people. I'm happy to dictate, but not if people are talking. I don't feel like talking over others. On a mission in Venus's atmosphere, again, on a mission in Venus's atmosphere, the Space Shuttle Magellan orbited the planet at a mean altitude of 361 kilometers. What is the orbital? So orbited the planet at a mean altitude of 361 kilometers. What is the orbital speed and the period? Okay? Again, this works for anything. Any body that's moving in some sort of circular motion around an orbit. So for example, we do sometimes use this for the Earth around the Sun, because the Earth around the Sun is pretty much a circle, like we were saying, even though it looks elliptical. The focal points are separate between the Sun and empty space, but you can almost approximate it for this to work with the Earth. But generally speaking, this is used for things like satellites that are going around the Earth. That's the major one of all. So for example, we talked about a geosynchronous satellite, which is like your cell phone satellite, that stays right above the Earth. And as the Earth rotates, the satellite also moves. So it moves at a constant velocity and keeps up with the Earth. So this application is widely used for satellites. It's also used on other missions on other planets. So like, for example here, when that Space Shuttle Magellan visited Venus, this was the actual height that it orbited at. And there was a reason for that. It orbited at this height so that it could stay in sync with the planet's rotational motion. So for example, when we figure out the orbital speed, there's a good chance that that orbital speed is the same thing that the planet is also rotating at. So if the orbital speed of the satellite is, let's say, 300,000 meters per second, which it easily could be, okay? It's moving, not 300,000, 300 meters per second. If it's rotating at that speed around the planet, and the planet happens to be rotating at the exact same tangential speed, then they move in tandem. And the satellite rotates around the planet like this. So as the planet moves, it looks as if the satellite's not moving at all. It's like what we're doing now. Whether you realize it or not, we're moving at a very, very high speed, a tangential speed, because the outside of the Earth is constant. Well, the Earth is constantly rotating at 15 degrees per hour, because there are 24 hours in a day and 360 degrees in one day. So it's 15 degrees per hour. That's how fast the Earth rotates. So every hour that goes by, the Earth rotates another 15 degrees, 15 degrees. We are moving at a certain velocity based on our location on the Earth also. We just don't feel it, because the Earth is also moving at the same velocity. The air around us, the atmosphere, everything's moving at the same velocity. So we don't notice it.
So that's why we don't get dizzy.
James? You sure? And that's why we don't get dizzy. Yes, very good. If we had like felt the force on us, okay, if we had felt this force, then it wouldn't work the same way.
How about why would it like earthquakes like that? Do we actually feel?
Earthquake is totally different. We're going to talk about earthquakes at a different point in time with energy. But earthquake has to do with the shaking and the tectonic plates rushing over each other.
Yeah, I know that. That's fine.
But this is not, earthquakes are not about rotation. You're still answering your question. Do eye contact, please. Karen.
Does that have to do with your point of reference?
It does. It always does, yes. So for example, if you're like on the surface versus on like the outer crust or like one of those layers, that's moving slower. And the core is technically not moving at all, the center point. Everything's moving around the core, right, of the Earth? So theoretically, it's always how far the radius is out, but determine how fast you're actually moving. It was just like the record player. Remember the record player? But it's moving very slow in the middle, really, but on the outside it's moving really fast to keep up. Okay?
No, that was a race car.
We did a race car, but we also showed like a record player. It shows a little thing you can move on the record disc.
Oh yeah, we did.
It was a really good drawing. All right. So for this problem, we're asked two things: the orbital speed and the period. So immediately, when you're looking at Kepler's 3 laws, first you're starting with orbital speed, which we call v. Okay, it is the tangential velocity, but the formula calls it v. So I'm not going to try and confuse anybody. And that equals gm over r. Okay, underneath the radical, very good. I was going to say to the 1/2 to trick you up there. Okay, gm over r to the 1/2 power, or it's square root 1/2 power.
You said it doesn't matter, right?
Doesn't matter. The orbital period, okay, if you remember, is 2 pi r cubed over gm here. Okay, r cubed over gm. You don't need the time symbol there. I'm putting it there to be, just to be nice. But gm, g is the gravitational constant. What is m again? Mass of what though? Sorry, depending on what scenario is here. This is not Earth. What would this one be? Venus. The central, let's use the word central object.
Wait, hold up.
Again, m is the mass. M is the mass of the central object. Remember, it doesn't matter if you have the moon or the Doppler radar that's above us or our cell phone satellite. Okay, m is only the mass of the central object. The outer object doesn't matter. Now, guys, whatever conversations you're having, end them now, please, because I'm getting a little frustrated already. We're only 5 minutes in and there's enough chatter. Let's all focus here so we stay on the same page. People are going to get lost and then you're going to get frustrated. So when you focus, it helps a lot. Here, g we know is a constant. Again, m is the mass of the central object. M is the mass, for in this case, of Venus, because it's a satellite revolving around Venus. Again, G is 6.67, 10 to the negative 11. The question becomes, in this problem, what is R? Okay, Julian.
So no longer doing what we did with the Earth. I just remember because we had the same thought.
For the one we did, we looked at the gravitational force between the Earth and another thing. We used G, M1, M2 over R squared. Sure.
I'm making sure it's like 2 different.
They are 2 different things. This is again an object orbiting around a central object. When we're looking for orbital speed and orbital period. When we're looking for the force between 2 objects, that's when we're using that formula. Bridget.
361 kilometers?
361 kilometers. That's the height. Yes. So we have to think though this, again, remember, here's Venus, here's Venus, here's the satellite out here. The height above Venus is 361 kilometers. But what's the actual distance between the center of the object now?
The radius plus 361.
Very good. Again, remember, the distance between this green dot in the center and the actual satellite is the radius of Venus now, not the Earth anymore, but Venus, plus this 361. Remember, what does R stand for? R stands for the mean radius. Mean radius means from the center of the center object to the outer object. So pretty much this R again is still distance between the two centers. Okay, it's called the mean radius, but in this case, you're calling it the mean radius because you're looking from the center of the center object all the way to the outer object. So now we're really looking at a path that follows something like this. Okay? Again, we're looking at the radius from the center object all the way out to the satellite. So we have, for this R now, for this problem we're about to complete here, we need to figure out, or we need to make a statement. And here's where we're going to make a statement on the side. Say that R is equal to the radius of Venus plus 361 kilometers. Make that statement somewhere. No, guys, again, this is not a new formula, but all we're doing is this. We're putting a little note on the side to remind ourselves that when we plug in for R here, we're not just plugging in the radius of Venus. We're not just plugging in 361. We're plugging in the combination of Venus's radius and the 361 together. Okay, remembering units though, because here the units of altitude are 361 kilometers. Again, 361 kilometers. The units of the radius of Venus has to be given to us. So, in your book, I want you to write this down, please. On page 250, so right down at the top, on page 250, you're going to see a data table. So if you're going to be doing any homework, which you will be doing, you're going to be using this data table for all that information. So if you want the radius of Venus, for example, here's Venus on the table I'm pointing to, and then I go to the mean radius, and it's given in meters. So because, again, convert this to meters, and you're given the other one in meters, and then you can just add them together. So on the side here, the radius of Venus happens to be 6.05 times 10 to the 6. And that's in meters. So I need to add this distance, which is right here again, from here to here, that's that distance, to 361,000. Remember, this is 361 kilometers. That's 361,000 meters. So this here, again, we say the radius is equal to, again, 6.05 times 10 to the 6 plus 361,000, and my units of this will be meters. Again, the actual radius for this problem is the radius of Venus right here, underlined in red, plus the altitude of the spacecraft, which is 361,000 meters. Because again, it was in kilometers earlier. Kilo means 1,000, so instead of 361, there's 361,000. So this is my actual radius now. Again, my R value is the sum of those two numbers. We have questions on this so far? Again, the idea is segment addition postulate here. You have one segment from the radius to the outer surface. You have another segment from the outer surface to the altitude of the actual spacecraft. These two segments sum together to give you the actual value of R. Okay, checking that, we get 6.41 times 10 to the 6. And again, that's in meters. So this will be the value that we're going to use for this problem. We really haven't even started doing the problem as far as velocity and period go, but now we have all of our numbers. Now we've got the radius. The mass of Venus I will give you, that's in the table. G is a constant, and that's all you need to solve these two formulas. Yeah, I would leave it a scientific notation here, yeah, just because it's going to get messy for you if you keep doing it the other way.
They always give you, so it's always going to be a given if you have like a question.
Sure, sure, absolutely. If you have a mass in the problem, you're going to be given it. Unless they give you everything else and say find the mass. They could give you the V and say solve for M, obviously. It's
Yeah,
solve.
but
You have to be given 3 out of 4, yeah,
Yeah.
absolutely. So here for this problem, we have the radius. The mass of Venus is given. The mass of Venus is given as 4.87 times 10 to the 24. And the units are kgs. That's the mass of Venus. I would just count the zeros. Count the spots. Spots over, right? So, Jude? Sure, I heard you. You said Mr. Howell.
Yeah, I got it.
Okay. So here, remember, the mass of the satellite is not even mentioned in this whole problem, because M stands for the mass of the central object, which is Venus. The mass of the satellite is independent. It does not matter in this problem. Again, this velocity, this period, it is independent of the mass of the object. It does not matter what the mass of the object is. So we've got these two values. Remember, this is a given. This is one of our gravitational constants. 6.67 times 10 negative 11. Remember that, please. And it's Newton meters squared per kg squared. Okay? 6.67 times 10 to the negative 11. Okay, always remember that, just like that. With these three numbers here, or these three values, you can then plug in and find those two. Again, take a look up here. If you go back to your formulas, look at your two formulas. You know G, you know M. Okay, start by multiplying these two. Then divide by the radius, or the mean distance, whatever we would call that. We call it the radius right now, or the mean distance. Divide by this number, take the square root. That's what you get for the velocity. Remember, it's all in scientific notation. Over here, you got to take the radius, or the mean radius, this value, and cube it. Again, you got to cube this first, then divide by the product of G and M. Okay, once you're done with that, you then got to take the square root and multiply by 2 pi. There are a lot of things to do here. Okay, again, you have to multiply all this stuff out, take the square root, then multiply by 2 pi. Here's one thing before I answer your question, Jordan, that I want to note. The velocity, hang on to it. The velocity here will be units of meters per second. Okay, meters per second. Just as all velocities and speeds are meters per second. The unit for the period is actually a time unit. And what time unit do we use? Seconds. So the units here are going to be seconds. Now, you're going to get a very large number probably, because the period of an object moving around Venus might be a large number of seconds. So if you want to convert that seconds into minutes and days, you can. Okay? You can always convert it into minutes, days, and hours also. So keep that in mind. Whatever we get as our answer in seconds, if you divide that by 60, then it's in minutes. If you divide that by 60, then it's in hours. If you divide that by 24, then it's in days. Okay? You keep going further and further, yeah. But again, your answer's in seconds, and that's fine, but keep in mind that it might be helpful to convert to get a reasonable answer. So if you have like some thousand amount of seconds, you want to know what that is in days, right? So your answer's reasonable.
So like in the test we should put this?
You should for what?
We should put
Would you
this.
tell us what?
Well, you might get a multiple choice, and maybe the multiple choice are in days.
Yeah, but I mean like if they asked us.
Doesn't
I mean,
matter.
like if we're taking the test, it doesn't really matter. As long as
It's for you to check. Now, what I do want to point out is this. If we solve this problem for the Earth, and we're looking at something, for example, like a geosynchronous satellite that rotates with the Earth, its rotation should be a period of 24 hours. Because the Earth rotates every 24 hours, it rotates once. Remember, the Earth rotates once every 24 hours. There's probably some decimals after, yes. Again, 24 hours is always an estimate, just like 365.24 is an estimate. So here, for this kind of a problem, we want to get our answer in seconds, then think logically does it make sense. What you end up getting for velocity of this problem, you end up getting 7.12 times 10 to the third meters per second. Or, if you want to write it as 7120 meters per second, approximately.
I got 7118.
Yeah, I got
7118.
Guys, that's fine. You got 7118?
Yeah.
That's probably right, actually. Then take a look. The book estimates your answer. God bless you. And 18 would round up to 20. Okay, 18 round up to 20. Did you multiply by 2 pi at the end? Now, what this means is really 5,660 seconds. That's too messy. Let's erase that. Let's take a look at this number now. If I want to convert this again, This is my answer in seconds of the planetary orbit. Okay, the orbit that the satellite is going around the planet. If I wanted to divide this by, if I want to convert this to minutes, I need to divide by 60. Okay, take this number, divide it by 60. What do you get when you divide this by 60? 94.3. Okay. Now, take a look at this answer, guys. What does this mean? This object, it spends an hour and a half. After an hour and a half, it's already been around the planet. Again, it's a satellite or some sort of a, in this case it is a satellite, but it's traveling the space shuttle around the planet in 90 minutes. In 90 minutes. If we were able to figure out Venus's rotation, and it turned out to be the same number, then it would be synchronous with the rotation of Venus. Again, if it took Venus 94 minutes to revolve, then this space shuttle would be moving with Venus. They would be moving in tandem, or they'd be moving in synchronous order. Now, if, say for example, the orbital time of Venus was 2 hours, then this is moving a little bit slower, or a little bit faster than Venus. Okay? Again, if the orbital speed of Venus was like 2 hours, then Venus goes a little bit slower. This goes a little bit faster. This could be more, though. So, for example, Venus's orbital time could be, 1 hour. We don't know. I mean, we do know, but we don't know off the top of our heads right now. We have to look it up.
Just like, if you were to ask a question where it's like, you wanted us to find whether the velocity and the rotation were the same, would you do that by like setting those equations equal to each other?
No. Velocity is a velocity. Rotation is a time period.
I mean, to find out like whether the rotation
was synchronous?
Yeah, synchronous.
You would have to find the value of that object that rotates. For example, the Earth. You have to take this and compare it to Earth's rotational period, which is 24 hours. So you need the rotational period of that central object. So you need to know how long does it take for Venus to rotate. Let's look it up, everybody. So in this problem, the space shuttle was moving in an orbital period that took an hour and a half to cover the entire planet of Venus. Let's take a look at Venus now and say to ourselves here, if we want to know what Venus orbital period is. It's probably just going to come up as orbital period. Here's Venus, for example. Venus takes 225 days for its orbital period. So Venus, again, Venus takes 225 days. That doesn't seem right. Let's take a look at actually what it means. Let's just look up Venus. Because that might mean the actual revolution. They might be making a mistake with a typo there. Wow, okay, yeah, so take a look. This is interesting. It says, take a listen, guys. Most planets rotate counterclockwise, but Venus rotates clockwise, called retrograde, once every 243 Earth days, by far the slowest rotational period of any planet. So that was it. So it takes 243 of our days for that planet to rotate once. It takes us, again, we're not talking about rotating around the sun. We're talking about the planet rotating on its axis. It takes us 24 hours for the Earth to rotate once. That's 1 day. 1 Venus day is 243 Earth days. It takes them 243 days for that planet to rotate just once. And then it revolves around the sun at the same time. Okay?
Yeah, we still have another.
So, several things. Several things, guys. First of all, Venus cannot inhabit life, so it wouldn't matter.
What?
You couldn't hear me because other people were talking. Come on, listen, guys. Venus cannot inhabit life, so it wouldn't matter, okay, whether the day of rotation is, first of all. Second of all, this is, again, not talking about how long it takes to revolve around the sun. It does not take about how long around the sun. We're talking about self-rotation, the inner object rotating. So for our example here, it takes 243 days for that Venus to rotate, but it took our satellite only 94 minutes to complete one entire surface like inspection, if you will. It went around the surface of Venus in 94 minutes. So this moved a lot faster than Venus was moving. So in this case, we would say that these two objects are not synchronous. I'm going to have to make a seating chart tomorrow, soon. I really am, because it's really getting me bad. I'm really upset right now. I'm not joking with you guys. Stop.
Okay, is it because of like what affects like other than like the what's it called the
I don't know the answer to your question. You're going to ask what affects the actual rotation. Is it closer to the sun? Is it further than the sun? The temperature? I don't know which one it is. Investigate. Okay? Because you asked the question a second. I knew you were going to ask. I'm not sure what depends on. It depends on the distribution of the mass of the planet. There's a lot of stuff. But right now we're focusing on this, okay? Just because it's going to take us on a tangent for a little while. That's a good question, Kenny, but I don't know the answer to it. Here's what I want to do. I want to work on one of these problems together, and then you work on the rest of them on your own. We're going to work on one of them together. I encourage you to do that.
I am not.
so would it be easy if I just put that?
Who listens to that? Oh yeah. Okay. All right. So let's take a look at number one.
There's so many exciting things I'm reading. Like, it's just a lot of Jose, Korea, there's a couple of
All right. So the period of Mars rotation is 24 hours, 37 minutes, and 23 seconds. At what altitude above Mars would a Mars stationary satellite orbit? Okay. Now, this is a tough problem because there's a lot of steps like we just talked about. The question becomes this to start. What is the problem? What is the problem actually asking for? Raise your hand and answer. What is it actually asking? Junior. Very good. Altitude. Now, remember, when we talk about a Mars stationary satellite, it's a satellite up in space. So here's our satellite out here. Here's Mars. We're trying to find the altitude. That's that distance right there. Now, relax. I know you have a lot of great thoughts. Relax for a second. We're trying to find that altitude. We also know that the real distance, though, includes the radius of the planet also. So in this problem, we have to consider the fact that we can solve for the whole thing, we can solve for this whole distance, and then subtract the radius to get what's left over. Okay? Again, we can solve for this whole distance, r, and then realize that the radius of the planet makes up for part of that distance, and get what's left over as an altitude. That's one way to do it. Another way to do it is in your formula to use Rm plus h for the altitude and just solve for h because you know what Rm is. So again, for this problem, we're told about the period of rotation, which is t. We're not given anything to do with velocity here. So right away we know we're going to use this formula to start. So when we have, in this case, r cubed over gm here. In this problem, it's very difficult to do this. And a lot of people try this, and it doesn't work. I'm trying to show you a little thing here. If you replace r with the radius of Mars plus the altitude, like this, because you can do this. You could do this. But take a look. You'd have to cube this, right? And you have a variable that's unknown. So you're talking about having a FOIL and then again FOIL afterward, or double distribute afterward. So this method, as much as it is correct because you want to solve for h, that's really what you're looking for, and you know Rm, is not going to help you too much. It's so much work. So what I encourage you to do is take a look at your first equation instead. Solve for r in the first equation, get an answer, and then simply at the end, subtract off whatever the radius of Mars is. Again, because we're looking for h, and this whole thing is really r. That's the key here. The entire distance is r. So if you can find out what r is, and you know the radius of Mars because it's in our table we'll be given, we can then just subtract that off to get the altitude. Okay, g is the gravitational constant, 6.67 times 10 to the negative 11.
Oh, yeah.
Very good. Now, what did say? Notice, units, units, units. Our units of time that we use are seconds. So in this case, for this problem, we have to convert our time, the 24 hours, 37 minutes, and 23 seconds, into a unit of seconds only. Seconds only. So, before we do anything, we have to start by converting this to seconds. We can plug that in for t at the end. We know g, that's a given. The mass of the central object is the mass of Mars. I'll give that to you. It's in a table. Okay, the mass of Mars in a table. And in this case, we're solving for r. So before we begin doing anything, let's solve this problem for r analytically. So divide by 2 pi, divide by 2 pi. You get t over 2 pi equals the square root of r cubed over gm. Okay, now, how do I get rid of the square root? Square both sides. Okay, square both sides. So this problem now becomes t over 2 pi squared equals r cubed over gm. Again, we're going from this line up top down to here. How do we get there? We square this side. If we square one side, we have to square the other side. The square and the square root cancel. This is what you're left with now. Again, we're solving for r. Getting rid of the gm, how do we do that? Multiply both sides by gm. Multiply both sides by gm. The gm's drop off on the right side. You're left with g m t over 2 pi cubed squared, squared equals r cubed. How do I get rid of a cube again now? Either cube rooted or 3 in the radical, it's cube root, or 1 over 3 power. The trick here is this. Once you get down to this line, you want to get rid of this cube. If it were a square, to get rid of a square, you take the square root. Square root. So here we're taking the cube root. Remember, the cube root is the same as the 1/3 power. That was from Algebra 2 last year. Okay? You're raising it to the 1/3 power. So this becomes g m t over 2 pi squared, this whole thing, all to the 1/3 power. That's what r ends up becoming. Okay, you can do this in the calculator, as long as you put the parentheses around the 1/3 when you enter in a power. Okay? GM, go back, take a look, Karen. You moved GM up first. You moved, you squared first, and then you move GM up. So you square this, then you move GM up. So you leave the GM outside, because it's not squared. Okay? Again, just go in the order. You got rid of the square first, then. If you wanted to, Karen, you could put the G and M under here as G squared M squared, because they would come back out as a GM, right? Or radical G, radical M, rather. Sorry. If you want to put the GM underneath, you got to put the GM under. There's a radical G and a radical M, because the radical G and radical M cancel with the square, giving you back G and M. But don't. It's not worth the time. So again, this whole problem, this is our final answer. Now we just got to plug in. We got to have a time. Capital T is the time period of orbit in seconds. G is given as a constant. M is the mass of, in this case, Venus. 2 pi is constants. You solve for r.
What's the mass?
Okay? We need to go to the mass of Mars here. So, sorry, I said Venus, sorry. The mass of Mars, 6.42. Mass of Mars, 6.42 times 10 to the 23rd. Okay, times 10 to the 23rd. Yes, kilograms. Mass is for planets is always going to be given in kilograms. So here, you're going to plug in the mass right there for m. You're going to plug in the gravitational constant. And the units are n. Sorry, not n. Oh no, it is n. nm squared. nm squared over kg squared. Okay, you're going to plug those in for g. The hard part is this. You need the t in seconds. So, how do I convert these? This is 23 seconds. So we're done with that conversion.
37 times 60.
Good. If I want to convert, remember dimensional analysis or common sense. If you have 37 minutes and you want that in seconds, multiply by 60 seconds per minute. So this, whatever this is just a product of 37 and 60. Okay? And over here, you have 24 hours. But there are 3,600 seconds in an hour. Where does that come from? I got to multiply by 60 and another 60. So to go from hours to minutes, I multiply by 60 minutes per hour. Then I want to go to seconds. I need to multiply by another 60. So it's 24 times 60 times 60 plus 37 times 60 plus 23, all units of seconds.
This is going to be on Facebook, right?
Okay, the recording, yes, absolutely. Again, all of this is in seconds. So whatever you get as an answer here is what you get for the value of t. So once you plug that in for t, you plug in the g value over here, you plug in the mass over here, you multiply through, simplify, raise it to the 1/3 power. Remember, on your calculator, 1/3 power needs to be in parentheses when you plug it in. So caret, parentheses, 1/3, close parentheses. Plug that all in, you'll get the value of r. Now, that's not your answer. Remember, what are we trying to figure out, guys?
Just
The altitude. So this is the distance between the center of Mars, and the satellite that's in orbit.
What's the radius?
Okay? We have to figure out the radius of Mars, or we have to make sure we know it. The radius of Mars for this problem, or for any problem really, the radius of Mars is 3.4 times 10 to the 6 meters. So when you get an answer, whatever you get as your answer, you need to subtract the radius of Mars to find out what that altitude actually is. Again, what does our problem look like? Here's what it looks like. You've got a satellite. It's a certain altitude. We'll call that h. It's got a radius. The radius is the radius of Mars. So we know that the radius of Mars and the height together make up the r value. So whatever you get for r, which I can tell you what you get as a number, whatever you end up getting for r, you have to subtract the radius of Mars. You end up getting, let's see, for the value of r, your answer here, before I subtract. Yep. 9.39 times 10 to the 7. Very good. Meters. This is the distance between the center of Mars and the satellite. So from this number, I now need to go ahead and subtract the radius of Mars from that. Again, this answer that we just solved for, this r value, is the distance between the center of Mars and the satellite. That's the r value we just got. So by segment addition postulate, we take the r value we got, we subtract rm, I'm pointing on the board if you want to look, you subtract rm and you'll get the h value. Again, we're finding the altitude. So take the r value, subtract off 3.4 times 10 to the 6, and you'll get the actual value. It doesn't do much to change it, to be honest. Good. And then your final answer here for the height or the altitude is 9.05 times 10 to the 7 meters. Again, where did I get that? You take the height or the actual distance here between the centers. You take that r value, you subtract the radius of Mars, and then you get the height above the surface. Notice, by the way, notice how far above the surface this object is. Okay, it's very far above the surface. It's not an object that is, happens to be just riding on the actual surface. We're talking times 10 to the 7 meters. So in this case, we're talking hundreds, I think it's a 900 million, right? 900 million, we got to go 7 spots. So in this case, it would be 9, 0, 5, 1, 2, 3, 4, 5. So I'm sorry, I apologize. We're looking at 90 million. About 90 million meters above the surface. Okay, 90 million meters above the surface there. Hold on. Byron and then Karen.
Is that formula that we use always going to get a formula for altitude?
This thing right here that we just did?
No, the formula over here.
To solve for r?
Yeah.
This is not altitude, but this is the distance between the center of the planet and the object.
So that's always like a firm.
If you solve for r, it's always going to be the same thing. Because you're solving, remember, Byron, you're solving this formula for r. So no matter what scenario, if you ever solve for r, you're always going to get this right here. So if you want to write that down as like a little note, you can, sure. Something good to know. But again, you can always get it where, Byron? From the original equation. Okay. We know that this distance that we got as an answer is this full distance, right? But we want to know what is the height here. So subtract the radius of Mars. It's up at the top right here. So take that number we got at the bottom right and subtract the radius of Mars up at the top left. I know it's a lot of writing, guys. There is a lot here, okay? Now, if you take a look at the second one says Pluto's moon, Charon, or Charon, I don't know how you would say that, has an orbital period of 153 hours. Very similar to this problem, 153 hours. Convert that hours into seconds. Then it says, how far is the moon from Pluto? So what are we looking for again? The height or the altitude. Again, it's the same problem, but it's worded differently. So you see how your examples are different wording completely? Okay, this is the kind of stuff that trips people up on the test. A lot of you guys know how to solve the problem, but I just word it differently. It's going to be happening that way all the time. So think about your wording. How far is it from Pluto? That's the height. That's this distance from the surface to the actual satellite, or to the moon. And a moon is a satellite. So for this problem, remember, time has to be in seconds. Excuse me. Time has to be in seconds here. You can figure out the mass of Pluto. I'll give that to you. You have to know it. And you need to know the mean radius of Pluto. So these are all going to come from your table values. Okay, once you get to the back, you're going to see that for these two problems, you're asked to find the velocity here. The velocity, or the orbital speed, v. So you're going to be using other formulas. So what I want you guys to do, I know there's not a ton of time left. Trust me, I understand that. I think there's only like 5 or 6 minutes left in the period. It's Monday, the period 4. There's only 5 minutes left. Try at least the second problem, and then tonight work on these two. Again, tonight you're going to be working on the back two here. Try the second one at least for now. I'm going to give you the values, I will. I'll give you the radius and the mass. Again, it's in your book.
I'm saying I did it analytically, so you want numbers?
For the second one? The second one is pretty much the exact same answer as this one analytically. So just plug in the new numbers and get the numerical value. Okay. Any other questions on this? Start the second one now. Try and get the same answer. Use the same stuff we did above here for the second one. Let me write down the numbers on the board before I go on.
Wait, do we want R or do we just want the apple?
What does it say, sir?
I don't know.
Read it. This is the mass of Pluto. You know what G is. Capital G is the same number again.
You're right. We don't leave the mass.
Okay, and you multiply that by... No, you gotta multiply the T over 2 pi squared. Basically, you just want to... I know. I'm not sure what number is the first one?
Yeah.
I have for time 88643. Well, you gotta divide. You gotta multiply your answer you got by the square of the quotient of T over 2 pi. Okay? That's fine. Again, guys, these values are all in your book tonight. So when you're doing the back, of this, we're talking about. Okay. Sorry, for number 3, I should let you know it says geostationary, so that means Earth. We're using Earth for number 3, so just write down a little note for number 3 that it's Earth. And number 4 is also Earth. Both of those values you're going to need, the radius and the mass of Earth, are in your book on page 250. I can write them on the board in a second. Okay? Let's start on the second problem still right now.
I don't know. I hate number 2. If you just don't know the variance.
You know how like
I'm not gonna say that.
I was using it this weekend, actually, I needed help for grading something.
Like,
Yes, Casey, do you have a hand up or not? I can't tell.
oh, Mr. How? I just asked Star. So, you know how we had to find R, so we don't have to know.
Because how many
we have
things
R.
are there?
You only have R for the.
It doesn't make sense.
Let me know what you get, Kevin. I'm arguing with this guy online.
What is that?
I ended up being
How far?
It's like, they changed.
What does it actually say? How far?
Yeah.
So here's Pluto right here, right? Here's the object. How far are they apart? What are you looking for? Gotta do all that work, solve for R, and then subtract the radius.
Don't do it.
I was gonna write it down. God.
For problem 3,
I know what I don't do it. But they said it's like multiply by 2.
this is in your book, people. This is in your book.
When you're ready, you